Welcome back. So let's go back to the forces of flight now. And after this introduction, historical introduction, let's discuss the more modern understanding of the forces of flight. So already Sir George Cayley in the turn of the 19th century, so 1800s, 100 years before powered flight, understood that these four forces were involved in flight: lift, drag, propulsion, and weight. So the aerodynamic forces of these four are, of course, lift and drag. Weight is just gravity, and propulsion will be generated sometimes by aerodynamic means and sometimes by other means, but the purely aerodynamic forces are lift and drag. So all aerodynamic forces are due to basically the integration of all shear stresses around the surfaces. So these aerodynamic forces are due to two things: the shear stresses and normal stresses. Or, in other words, viscous effects, shear stresses, and pressure, normal stresses. So a typical stress distribution would look like this. In the case of the pressure, we might have around a wing or airfoil some distribution of negative pressure, and this was already understood by Sir George Cayley, that you would have a low pressure area on the top of the wing, and a positive pressure in the leading edge and the bottom. So the distribution of pressure, a typical distribution of pressure might look like this picture over here. Pressure less than zero with respect to atmospheric, of course, at the top, and greater than zero at the bottom. A shear stress distribution will vary in magnitude around the airfoil in some sort of way, and we don't know the distribution, and the these normal stresses plus the shear stresses, viscous effects, will produce a resultant aerodynamic forces, which we simply decompose in two forces: one perpendicular to the velocity, and we call that lift, perpendicular to v, the velocity of flight or the velocity of the air around the object, and drag, which is a force parallel to the velocity. Now, if you think about this picture of the aerodynamic forces being produced by this distributed shear around the wing, then of course, these both P and shear stress will vary in magnitude. Pressure will also vary in direction. Well, they both vary in direction with respect to any reference frame. And so their integrated effects produces a resultant force, and you can see that it would be very hard to actually know the shear stress and pressure to be able to obtain the lift and drag. I would volunteer that the only way to actually know these is through computational fluid dynamics. If you're able to actually calculate in detail the solution to Navier-Stokes equations around an object and to obtain a measure of all the stresses in every point, then you might be able to integrate those and obtain the forces. But in general, you can see that it would be very difficult to actually know these. But nevertheless, let's move on and see how this would look like if we want to make a mathematical description of these forces. So to do that, let's consider a small element of area. on an airfoil or wing or object. And suppose that we have in our reference frame, x and y, we have a velocity in the x direction. Let's call it v. And we have some element of area. Just going to draw the element of area here. So element of area, call it dA. And we have the two forces, stresses, a normal stress, and that's P, so the force is going to be P times dA, and the tangential stress, so that the tangential force is going to be tau dA. And let's say this thing here makes an angle of theta with respect to the x-axis. So now we could write the components of the fluid force. In both the x and y direction. In the x direction, what goes in the x direction? Let's see, with respect to the angle theta, P goes in this direction. So in the x direction, it's going to be P times the cosine. So P dA is the force times the cosine of theta. That's the contribution of the pressure. And we also have a contribution due to the shear. Let's call it, okay, that's the shear at the wall. And so the shear is a vector in this direction, right, tangential. And this is going to be, let's see, this is perpendicular to that one. And so if I draw a vertical, that's going to be perpendicular to that one. And here's theta again. So this is shear, this is P. Then our x direction, the force in the x direction is tau dA times the sine of theta, component here. In the y direction, also we have a contribution from the pressure and the shear stress, but the contribution from the pressure is negative with respect to our y direction, so minus P dA sine theta and plus tau dA cosine theta. So if we wanted to calculate, we consider now, we look back again that our velocity is parallel to the x-axis, so lift and drag are parallel and perpendicular to the x-axis. So drag is the integral of the force in the x direction, and that's going to be the integral of P cosine theta dA plus integral of tau sine theta dA. The lift is the integral of the vertical force, and that's minus integral of P sine theta dA plus integral of tau cosine theta dA. So you see here that to integrate this, we would need not only the information about theta at every single point in the surface, but we also need the shear and pressure at every point. And this is what's very hard to know, P and tau at every point. So because it is so difficult to know these things, unless we do a very detailed simulation, computational simulation, and even so there might be some errors or something, and or it might be difficult to obtain or require a lot of computational power, then it turns out that most of the work, engineering work around this topic revolves around empirical results. And so we work with experiments, and we use what's called the coefficient of lift and coefficient of drag to calculate these forces from empirical observations, because this, as I said, is very difficult to know. So we use instead the coefficients of drag and coefficient of lift to calculate these forces, and those are obtained empirically. Lift and drag coefficients, we define them as follows. Basically, through non-dimensionalization, we define the coefficient of lift as the force of lift non-dimensionalized by the dynamic pressure 1/2 rho v squared times the area of the wing, some characteristic area, and the coefficient of drag, similarly, the drag force divided by 1/2 rho v squared times the area. And then these guys are obtained most often by experiments. So, for example, you could have, for a particular wing, a plot that shows, in this case, the coefficient of lift. In this example that I've collected here, the coefficient of lift for a particular airfoil. Here in the blue, you might have a lift that increases with the angle. So to remind you of the nomenclature of an airfoil, we have the chord is this distance here, oops, and the angle between there's a line between the leading edge and the trailing edge. The angle of that line is called the angle of attack, and normally the plots of lift coefficient are provided with respect to the angle of attack. So we could have, let me try to draw a not a little bit shaky, but nevertheless. So this is the angle of attack, where most usually we use the Greek letter alpha for the angle of attack. The angle formed between the chord of the airfoil and the relative wind. And here we have the situation for a regular airfoil in which the lift coefficient increases with angle of attack up to a point where separation occurs. We'll discuss separation a little bit more in a moment, but there's a point, the angle, normally the air will conform to the curvature around the airfoil without problems, like so. But there comes a point where the angle is such that there is separation and the air is not able to follow the curvature around the airfoil, and this is called stall. And this is what we see here. That at some point the lift coefficient does not increase any longer, it reaches the maximum, and beyond that point the lift coefficient suddenly drops. The airfoil is no longer capable of generating lift because of the phenomenon of separation. Other things that you will normally observe in a plot of lift coefficient are the effect of what are called the high lift devices. For example, flaps are and slats are high. This is a slat over here, something that extends from the leading edge of an airfoil forward and changes the curvature overall of the wing. And flaps are here in the back. Also, they change the curvature of the wing. These are basically high lift devices. We'll return to this again. I'm just introducing some concepts at the moment. We'll return to discuss this in more detail when we concentrate on the force of lift in next class. But the main idea that I wanted to communicate at this point is that lift coefficient and drag coefficient are going to be provided through experiments, because obtaining the forces, the aerodynamics forces exactly, it would be very difficult. It would require us to know the pressure and wall shear stress at every point. Okay, so we'll discuss a little bit more qualitatively some aspects, and then we'll revisit them a little bit more rigorously later on. So let's discuss some characteristics of external flow. And the first thing that we need to note is that the characteristics of the flow will depend on the shape of the body, and we distinguish between two types of bodies when we are discussing aerodynamic forces. The streamlined bodies, which are wings and airfoils, and bluff bodies. Bluff bodies is a term that we use for anything that isn't streamlined, that put some sort of obstacle to the flow and will be followed by what we call a wake. So we have here the wake, and the wake is generally a very disordered flow with concentrations of eddies of different sizes that interact, very unsteady flow. And this characteristic of bluff bodies is what we call separation. So we'll discuss this a little bit more. For example, a cylinder, a ball, all of these objects are bluff bodies. So let's discuss this guy a little bit more, bluff bodies. So for example, a cylinder or a ball. Like in the case of an airfoil or a flat plate, the flow will vary with Reynolds number. And if you remember when we introduced the terminology, the concept of boundary layer, we said for increasing Reynolds numbers, you will have a boundary layer which is thinner and thinner. And the same thing applies for a bluff body, in the sense that if you have a low Reynolds number, so the flow depends on Reynolds number in a similar way. Give me a moment because my computer's not responding. There it is. Depends on Reynolds number, like for the case of a flat plate, but it has the additional feature, which is separation. So, first for low Reynolds, similar to the case with a flat plate, we'll have viscous effects important in a large area or several diameters away. If it's a cylinder flow, would have viscous effects extending several cylinder diameters away. So this is the case I'm discussing. Viscous effects are important. Several diameters in any direction. From the cylinder. And we discussed before creeping flow, if you recall. For creeping flow, we would have a situation similar to this, where The effect of the presence of this body is felt in a very large domain, in a very large area of fluid. In the case of creeping flow, the streamlines would be symmetrical, similar to what has been drawn here. And that's the case for low Reynolds number. As you increase the Reynolds number, then the confines of the effect of viscosity are going to be narrower and narrower. Basically, the boundary layer becomes narrow. Here is a situation with a moderate Reynolds number where already beyond a certain distance away from the object, there is no viscous effect. There's no, the flow doesn't feel the presence of the object. This is as you increase Reynolds numbers. So basically, larger Reynolds numbers are associated with thinner boundary layers in the case of flat plate, and in the case of a bluff body, with the viscous effects being confined to distances closer to the body, except for the case of this separation. For this case of even higher Reynolds number, you will have a thin boundary layer, like in the case of the flat plate. But there is a point beyond which there's flow separation. So even though viscous effects are important, so even though the boundary layer is very thin, there's still a region where that extends far away from the object, where viscous effects are important, and this is due to separation. This is the additional feature of flow around bluff objects. So note that we could say that always viscous effects are confined to the boundary layer and the wake. The wake is a separated region. Boundary layer and wake. And separation is a crucial concept. So let's concentrate on this a little bit more. Yes?
Is the boundary layer still described as a gray shaded area in the second drawing?
Yes, but up to the boundary layer up to here, up to the point of separation, is similar to a boundary layer as we know it from the flat plate discussion. But beyond this point, it's what we call the wake, because it's no longer a thin region near the body. It's actually a very large region, and it's due to the fact that there's recirculation areas around here, because the flow is not able to follow this curved path all the way to the back. So let's discuss this idea a little bit more. So this is related to the effects of a pressure gradient. And so as with the case of the flat plate, as I was saying, boundary layers are normally thin, okay? But the pressure gradient is not zero for a curved object. In the flat plate, if you recall our discussion of the boundary layer, we came to the conclusion that the pressure gradient was zero. The pressure actually was constant throughout. And did mention there briefly that this didn't apply if you have a curved surface, because basically the argument that we made, if you recall, was that our neglecting of various terms resulted in the conclusion that the pressure was going to be dictated by the inviscid area. And in the inviscid area, the pressure changes according to Bernoulli's equation. So if there are no curved streamlines, there is no change in pressure. And so the pressure was constant everywhere. But in here, there are curved streamlines because the body is curved and the flow must adapt to the body. And so there are going to be pressure changes, unlike the flat plate. So unlike flat plate, pressure gradient is not zero. Because the body is curved. So the effect of the curved streamlines is that there's going to be a pressure change. So in fact, the free stream velocity is not constant because it needs to adapt to the curved body. And so if you recall this discussion that outside the boundary layer, the flow was behaving like as if it was inviscid. So in this case, what we have, because of the curved streamlines, we have that the free stream velocity is changing and the pressure is changing according to Bernoulli's equation, and all of that pressure changes extend all the way inside to the boundary layer. And so to discuss this a little bit more, consider the flow around the cylinder, and in the completely inviscid case, right? There's no boundary layer, nothing, the completely inviscid case. We did not discuss in this course potential flow, which is the field of fluid dynamics which refers to completely inviscid flow. But it is possible in that case to get a lot of actually analytic results. It's quite a mathematical sort of branch of fluid mechanics, and it is normally covered in a more advanced fluid mechanics course. But you are able to obtain analytical results. And these analytical results allow you to obtain the actual free stream velocity for this situation, a flow around a cylinder, with, suppose in this case we have upstream conditions of velocity u, capital U, and pressure P naught, approaching a cylinder. So if the fluid were inviscid, Reynolds equals infinity, then the streamlines would be symmetrical as drawn in this sketch around the cylinder, but the velocity changes. Remember, there's a stagnation point, so in fact the velocity reaches zero at one point. So there's a variation of velocity, quite substantial variation of velocity from zero, the stagnation point. It is capital U at free stream, and it reaches a maximum velocity which is actually known to be 2u from potential theory results at this point here of what is it? How do we measure theta? That's 90. Theta equals 90 degrees. So velocity varies from 0. Let me put the bar there to distinguish at the stagnation point to the value 2u, u being the unperturbed free stream, at that point of theta equal. So this point here has a velocity 2u, capital U, and this point of course has velocity equal to 0. Stagnation point, there's also another stagnation point in the back, velocity equal to 0, and this one has velocity 2u. So there's quite a bit of variation in velocity, and therefore Bernoulli's equation, this is inviscid, and there's also variation in pressure. The maximum pressure is as you know, is the pressure at the stagnation point. So what is the maximum pressure? The stagnation pressure. Anybody remember stagnation pressure? P naught plus the dynamic, which is, very good, 1/2 rho u, in this case I called it u squared. That's our maximum pressure, the pressure at the stagnation point. And the minimum pressure It is found at the point of maximum velocity, which is the very top and the very bottom of the cylinder. Points C, and I didn't call this one, but the same thing happens there at the bottom, is actually a result also can be obtained from potential flow analysis, and I'll just write it down and ask you to believe me. 3/2 rho u squared. This is at the top and bottom, and this is from potential flow analysis. Potential flow is the branch of fluid mechanics that is dedicated to inviscid and irrotational flow, fluid that doesn't have any vortices in it. And we don't cover that in this course. Because the flow cannot go through the body, right? So there's still the no-through boundary condition, despite the fact that we don't require the no-slip boundary condition to be satisfied. There is a slip velocity, and we don't care. We don't impose no-slip. We do have to impose no-through boundary condition. The vertical component of velocity at the boundary has to be 0, because it's an impermeable boundary. So the flow has to adapt somehow and go around the object. It's an obstacle. But the way it goes around is with slip, and so it recovers completely and the streamlines are symmetrical. That's the case of inviscid flow. But you see that what I was trying to illustrate in this discussion is this situation, which is that the pressure varies from a maximum value at the stagnation point to a minimum value at the point of 90 degrees and back to a maximum at the stagnation point if we follow that streamline that's right on the cylinder. And the velocity, on the other hand, varies from a minimum at the stagnation point, in fact 0, to a maximum at the point of 90 degrees and then back to 0 at the back stagnation point. This is all the inviscid case. Now, in the viscous case, even with very, very small viscosity, of course, the drag can never be 0, right? So, because of in the viscous case, we have no slip. Which means that the velocity is equal to 0 at the wall. So drag is different than 0 always, even if the viscosity was very small. So this is the case for, if you now, to this picture that we've drawn here, we add viscosity, is the following. I'm just giving a little time for, okay, some note takers. So if we add some viscosity, then the pressure distribution that we had from the inviscid case transfers over to this case without any changes, because the same argument that we made during the boundary layer discussion. So the pressure distribution of the inviscid flow around the object is imposed now on the viscous flow inside the boundary layer. The only difference is that we have the no-slip boundary condition. So the flow in the boundary layer must adapt to, change rapidly from the value, from a given value free stream to 0 through this velocity gradient. Okay? And what we have is that if we're looking at the same situation that we had before, a particle going from point A to point C at the top, 90-degree angle, back to point F. Previously, we had that particle going all the way around without any loss whatsoever. Now, because of viscous effects, the particle is going to experience a loss of energy due to friction. And so as it is going around from A to B, to B and C, right, then as it continues around the cylinder, it loses energy due to friction, and it's going to run out of kinetic energy, if you will, and be unable to reach the point F, and will not have enough energy to complete the turn and separate at some point, forming the wake. That's the idea that I wanted to propose to you. So the first ingredient in this picture is that the pressure distribution that we just discussed previously for an inviscid flow is imposed in this case. Pressure distribution that we just discussed for inviscid flow is imposed on the viscous flow inside the boundary layer. This is a direct result of the discussion that we had before about boundary layers, where we neglected some terms in the Navier-Stokes equation and discovered that the pressure had to be the free stream pressure. For the flat plate, it was constant. For the curved object, it's not a constant, but it's still the inviscid pressure. So we distinguish, because of this discussion, we distinguish between, so let's introduce two new terminology. We call a favorable pressure gradient dpdx. If we're looking, imagine now I'm talking about this area very close to the wall, and we're looking at the boundary layer. So forget about the curve and imagine that we're looking at a flat plate, and that's the dpdx I'm talking about. If dpdx were less than 0 along a surface, then pressure decreases in the direction of flow, and that's a favorable pressure gradient. So along a surface, let's be clear. Pressure decreases, and that's called a favorable pressure gradient. And we talk about an adverse pressure gradient. Adverse pressure gradient when dpdx is greater than 0. So along the surface, the pressure is increasing. So basically, here in the back, the pressure is increasing. Let me just quickly flash the previous image, okay? This is the inviscid flow. Pressure went from a maximum at the stagnation point to a minimum value at the point of 90 degrees, and then started increasing again as it went around the back, remember? And that pressure distribution is imposed in this viscous case in the same way. So pressure is going from a maximum here to a minimum at point C, and then it's increasing again in the back. So it's a favorable pressure gradient in the front side of the cylinder and an adverse pressure gradient in the back of the cylinder. This is dpdx greater than 0 along the surface in the back, right? This is the back of the cylinder case. So a particle moving from A all the way to F will experience a favorable pressure gradient as it goes from A to C, and then experiences an adverse pressure gradient as it goes from C to F. And that adverse pressure gradient has the effect of basically the particle needs to flow against that pressure gradient, and eventually it runs out of energy as it's going against the pressure, and at one point it just has to separate. It doesn't have enough kinetic energy to go all the way around to point F and recover completely because of the effect of viscosity, friction. So fluid particle going around, say, past point C in the very top, is flowing against an adverse pressure gradient. It runs out of energy eventually, and it has to separate. This is called boundary layer separation. Beyond the point of separation, there's this reverse flow and the wake. This boundary layer separation, let me just finish this idea, and this is a bit loose here to say, it runs out of energy and it separates. Over here, point D in our cartoon. This is called boundary layer separation. Beyond the boundary layer separation, there is reverse flow in what we call the wake. And this reverse flow results in an average pressure in the rear of the cylinder, which is much lower than we would anticipate, much lower than in the front half. And this produces an added effect of drag, which we call the pressure drag. Pressure drag. And no matter how small the viscosity, pressure drag is always present because of this effect that I just described. The friction, makes sort of like there's some added effect of viscosity there fighting with inertia. The particle in the end runs out of inertia, is not able to go all the way around to point F. It separates, produces reverse flow in the wake. Reverse flow produces pressure drag. This is always the case regardless of how small the viscosity might be. And so this is the reason why there's always a large drag around bluff bodies, which you wouldn't encounter in aerodynamics body. This is a source of a large force of drag. And separation is always associated with drag. In fact, when we look at aerodynamic streamlined objects, beyond a certain angle of attack, I was saying, the flow will also separate. So it depends, even an aerodynamic shape will behave like a bluff body if the angle of attack is large enough. I just want to show you the case of aerodynamic bodies in which you have a similar situation to the cylinder we were talking about but normally if the angle of attack is small, the particles of fluids are actually able to go all the way to the trailing edge without separation. Beyond a certain angle of attack, the particles of fluid are not able to go all the way to the trailing edge, and they separate somewhere around here, producing, here it's called a separation bubble, if you can't see that, and this increases the drag immediately, decreases the capacity of the airfoil to generate lift, and eventually is what we call stall. And regardless of how small the viscosity, this effect is always present. Okay, so next class we're going to discuss in more details drag and lift.